Okay, so welcome to the basics of nuclear decay. And it's not nearly as complicated or dangerous as some of the hype or some of the social media posts or movies like the Chernobyl might lead you to believe. Of course, these are all matters of scale, but we're going to keep it on a very small scale. So what we're interested in is these 5 types of radioactive decay. You'll want to familiarize yourselves with their names and what they do. These are the Greek alphabet of ABC, alpha, beta, gamma, are the first 3 letters of the Greek alphabet. And the way I keep track of it is in terms of their size. Alpha is the biggest, beta is the middle, and gamma is the smallest emission. In fact, you might say that a gamma emission is nothing but pure energy. We also have something called a positron emission, which is exactly the opposite of a beta emission. We'll get to what they look like in a little bit. And finally, something called electron capture. All right? So you want to try to keep these as straightforward as you can. And our alpha emission, I'm not really good at writing Greek letters. This is simply a helium nucleus. And they even write it like that. A helium nucleus, where helium has an atomic number of 4 and 2 protons. We have what's called a beta emission, and this really is just an electron. An electron is simply a negatively charged particle. So the way they write that is, it's an electron. It has a mass number of 0, and it is the charge equivalent of a proton, but it is negative. What we call a gamma emission, it's not really a particle at all. It's simply energy. And that means that it has no mass nor charge. It's just energy. Okay? A positron emission, it is the reverse of an electron. You could call it a reverse electron. And some people have even written it as E positive. But that's kind of a mind bender, so I never write it like that. A lot of them will just simply write that it is an electron with a charge equivalent to 1 proton. And finally, something called electron capture. It's simply when a nucleus absorbs an electron. Okay? So when you're doing this, you're going to want to keep the atomic mass and the atomic number handy. And it's probably a good idea to have a periodic table, because you're going to need to quickly identify the atomic number. That's, this guy. Sorry, this one's such a crappy one. Magnesium's got an atomic number of 12 and a mass of, on average, 24.3 atomic mass units. All right, so here's what this looks like when they ask us to try this. This is a problem I would have assigned in more normal times. This is number 11. And when it says write an equation describing the radioactive decay of each of the following nuclides. A nuclide is simply a nucleus of various isotopes with various atomic masses, right? And there are different numbers of neutrons and whatever. Okay. So it says write an equation describing the radioactive decay of each of the following nuclides, and the particle produced is shown in parentheses, except for electron capture, where an electron is a reactant. So this is what I would ask you to do. I'd say, okay, what would happen if a nucleus of hydrogen, what we call tritium, with an atomic mass of 3, which is kind of weird because hydrogen should simply be 1, undergoes beta emissions. So remember that a beta particle, for this one, a beta particle is simply an electron. It's the middle one, and it looks like this. It has the symbol for an electron, a mass number of 0, and a charge number of -1. So what happens when this decays? So we are going to give off an electron, and this is going to be kind of weird, but our other product, we're simply going to make the transfer using the mass and the atomic number. So what happens when you give off a mass number of 0? You have an atomic mass of 3. And what happens if you lose -1, right? If you subtract -1, you get an atomic number of 2. Well, there's only one element that has an atomic number of 2, and that would be helium. So this is what an equation for nuclear decay looks like. All right. So part B would say, okay, we've got a nucleus of lithium, and it's going to undergo beta emission followed by alpha emission. So the first thing that's going to happen is we're going to lose a beta particle. We're going to lose an electron. That's going to result in no change for the atomic mass, but it will add the equivalent of a proton to the nucleus. So you want to be able to tell us what element has an atomic number of 4, and there's our old buddy carbon. Excuse me, not carbon. I need a better one of these. This one's crappy. That is beryllium with an atomic number of 4. So if we lose this, someone is asking a question about the lab. We'll get to that in a little bit. If we lose the equivalent of an electron from our atomic number, and our atomic number goes up by 1, now this is beryllium. Okay, now according to this one, there's a second part to this problem where this resulting nuclide from the first emission is going to undergo alpha emission. So our nuclide of beryllium with an atomic mass of 8 and an atomic number of 4 is now going to undergo alpha emission. That's where we lose the equivalent of a helium nucleus. And so what that's going to result in is we're going to drop our atomic mass by 4, and we're going to drop our, our atomic number by 2. So this is now another atom of helium. Okay? That's all we do. So I will leave you to try these next 2, and I will post the answer key for you. All right? The next thing we want to be looking at is something called half-life. So the premise of half-life, what we call half-life, is how long does it take for our sample to lose exactly 1/2 of its mass to decay. In other words, how long does it take for it just to disappear? And you know that some elements are way more unstable than others. If you look on the periodic table, that will be elements that are larger, and they tend to be elements here in this very bottom row. Here, it's right here in this name, radium. Okay, so anything that's really big has a tendency to be unstable. Here's a couple of more famous elements, uranium and plutonium. So if you've ever seen the movie Back to the Future, and that means that they decay rapidly. Well, what does rapidly mean? What we mean by rate of decay is how many decay events per hour take place. And we're going to call this, since it's a rate and since it's a constant, we'll call this, if you remember, I told you to brush up on your rate law, we'll call this the rate constant. And we used to represent this with a lowercase k. And so here's how we get into half-life. This is always a first order reaction, this decay of any radioactive substance, any radioactive nuclide is always a first order reaction. And that means, now if you reviewed your rate law like I asked you to, that the half-life for any reaction is equal to 0.693 over our rate constant K. Here's how we use this. This is another problem I would have assigned in normaler times. It says the rate constant for a certain radioactive nuclide is 1 times 10 to the negative third decay events per hour. That's why hours is in -1. So we have 1 times 10 to the negative third decays. Trying to write, ladies and gentlemen. And it doesn't like this. Right up there. Decays per hour. What is the half-life of this particular reaction? In other words, how long does it take for half of whatever the mass is to decay to something else? 0.693 over the rate constant K. Well, we know the rate constant K. In this case, it's 1 times 10 to the negative third hours to the -1. So let's bust out our fancy dancy schmancy calculator. And we'll say, what is the half-life? 0.693 divided by 1 times 10 to the negative, 1 times 10 to the negative third. And this is our answer. It takes 693 hours for whatever our massive sample to decay to half of its original amount. Okay? The greater the rate of decay, the hotter the sample. So what I'd like you guys to try is this one, number 25, where it says krypton consists of several radioactive isotopes, some of which are listed in the following table. The half-lives are here. 27 seconds for this first sample, 11.5 minutes, 14.8 hours, and 2.1 times 10 to the fifth. That's 21,000 years. So which one is hottest? The one with the greatest rate of decay. And remember that when you're doing this, 87.5, well, that's, you know, not 50%, not 25%, but we've lost 12.5%. So how long does it take for 87.5% of each isotope to decay? So 87.5 would be, obviously, 50% is 1 half-life. And then when you lose another, you're down to 25%. And then when you lose another half, you're down to 12.5%. So give that a try, please.